linear algebra student. This video is for chapter 1.9, part 2. Continue with standard matrix with some transformation, but 2 steps. So we didn't finish this. So in this particular example, where we do a reflection and then reflect over the x1 axis and then reflect through x2 equal to x1. So we would do the 1, 0 matrix E1 and then the 0, 1 matrix. Okay, so this is 0, 1 matrix, and the first step, if you reflect it, it becomes 0, -1, right? And then we say the second step, which is reflect over x equal to y, is you switch x and y, so it becomes -1, 0. So the standard matrix will be T of E1 becomes 0, 1, and T of E2 is -1, 0 over here, right? These two. So this would be the standard matrix. So you can just do this once. Even if you have 2 steps, you don't have to construct 2 matrix side by side. You just construct one by doing by having 1, 0 and 0, 1 following the 2 steps. And that's the standard matrix. So, so we'll have this put aside. This is quite interesting, and I think particularly interesting is how you can construct the rotation, like what we did last time, and a lot of the thing. And it is very useful when you program. If you extend it to x3, you can, program movements of pixels on the screen on a computer. That's what they use the matrix for. Okay, we're going to switch gear to something new. When we talk about linear transformation, no, this is not linear transformation. It is about, is this for linear transformation or actually just transformation? Let me look at this. So there is a new definition. The definition is not limited to linear transformation. They would define something for a mapping T from N to M. It is called a onto mapping if each B has at least 1 in Rn. So that means there's a lot of X here, right? A lot of X. This is the input. And then for some reason, they would map into this is Rm. And every single B here, all of these B here, actually can be mapped by these, okay? So yeah, each one of them mapped to one, or they could map to multiple. But anyway, every single B in Rm had a pre-image. So each B is the image of something. So it is not onto if you can find some B such that there is no mapping, right? So if this is very big, say for example, this one is really, really big, and all the X only go to part of Rm, then it is not onto. Onto means every single B can be mapped from X, and we call it onto. So, well, the space is actually for that. If it is, so not onto would be like this. Not onto would be you have some part. So these are the one that can map from the X. The X only maps in this side. So they go to all this B1, B2, all this B, but this one has nothing. They cannot be mapped from X. X cannot maps here. So this is not onto. But for onto, so this is a T. All this rule will allow this X, there's a lot of X, right? X1, X2, blah, blah, blah. Not just one vector, but just different vectors. And somehow it could be whatever. It maps to every single one. Okay. B1, B2, B3. So, and all this B actually consists of Rm. So this is Rm. So only part of Rm. So this is the range. The range is not Rm, but here the range is the Rm. You for everyone that you look at, you can see a X that go into it, right? Like that. So that's onto, something onto it. And then another definition as a new term is called one-to-one mapping. One-to-one mapping is, say, if you have a mapping, doesn't have to be linear transformation, but it's one-to-one if each B in the image, so it doesn't have to be the whole thing, but if I have a B, there's only one X. All the B can only have one X. So let's do a not one-to-one. Not one-to-one would means some of them, this is just one. So this is B1, B2, there's a lot of images, right? There is at least one, maybe multiple, where it is mapped by 2x. This one, x1, and this both of them go to it. So that is not one-to-one, right? x1 and x2 have the same B. Or you can say B1 actually was from two different x. Not have to be everyone. So long as you can find one that is not one-to-one. Whereas one-to-one is, if this is a lot of different x in the domain, and there's a lot of different b in the range, every single one of them is just one by one, right? They don't share b and they don't share the x. They pair up one-to-one. So if you look at 1b, there's only one x. There's not another x that goes into it. So this is one-to-one. So technically one-to-one. So this is the definition for mapping. Okay, so we can actually say, well, let's do a transformation by a matrix of AX. And we want to see if this is a onto, and also if it is a one-to-one. Onto means what? Onto means every single R3. So that means if I have A times, it's for R4, right? X1, X2, X3, X4 equal to B1, B2, B3, right? Because we are combining all these X1, X2 together to find a linear combination of these columns to these. So we would say AX equal to B must have solution because all of R3 actually is being covered, has solution. And do you still remember when we say that AX equal to B has solution and it has to be consistent and not has solution? We can use theorem 4. Theorem 4 means A has a perfect position in every row. So what we can do is look at the perfect position. So here A has a perfect position here because this is already reduced, not reduced row echelon, but row echelon form. So this one. So every row had a perfect position. There is no possibility of having 0, 0, 0, 0, and then a contradiction. So that is a solution because the all rows has perfect position. So when you are to look at onto, it is easy to check that the rows, okay? Because based on theorem 4, if A has a perfect position in every row, then AX equal to B has solution. These are all equivalent. Is T one-to-one? One-to-one means AX equal to B. Every single one of them can be solved, right? Can be solved by, has a unique solution, one solution. So how do I know if it has one solution? So maybe we can actually just do the row echelon form of A to see what happened. See if, here, 100, negative 420. Did I enter it? I think I did not. Okay. No. Okay, so do new matrix. One more row, two more column, is it? Yeah. So let's say 100, negative 420. Negative 420. 8, negative 1, 0. And then 1, 3, 5. So we want to do row echelon of D. Okay, so let's do reduce row echelon of D. So what happened? It is, yeah, it is, we have 3 position, and then, well, actually, does it have one solution? No. You can see that there is a free column, right? So there cannot be a cannot be one solution. It's not possible because we have 4 columns and we have R for R3, so there must be multiple solutions, not possible because there is one free column, one free variable. To solve it, you have 4x, right? And there's one free variable. So actually, in a reduced row echelon form is what was it? 1060, 1060, and then 1 negative point negative 1/2 well 0 1 negative 1 negative 1/2 0, and it's a 0 1 0 0 1 0. Is it 0? No, 0 0 0 1 0 1. So this perfect column, but this is a free column. So there's more than one solution. It's not 1 to 1. Okay, so that's what it is. I'm going to stop here and look at, in the next video, we'll talk about an other theorem that can help us to solve onto and 1 to 1 without actually going through that much hassle. Yeah.